So you guys are all here tonight to see Henry Reich. He is the founder and host of MinutePhysics. So he makes YouTube videos for a living. This started, well, the passions arose back when he attended Grinnell College and majored in physics and math. From there, he obtained a master's from the Perimeter Institute for Theoretical Physics in Waterloo, Ontario. In addition to his interests in physics and math, he's also always been interested in videography and filmmaking and art. So he decided to combine those two passions into this wonderful YouTube channel called MinutePhysics. So tonight, Henry will be talking about the physics of free will, and I think I speak for all of us when I say I'm really interested in hearing what he has to say. So please give it up for Henry Reich.
Can you all hear me? Is this thing loud enough? Is that working? In the back, can you hear me? Sounds good. All right. Let's see if we can get this thing to turn on. There we go. Apologize, the projector seems to have a problem displaying colors in alignment, but most of the talk's in black and white anyway, so it doesn't matter. If you came to this talk tonight, you probably had to make a decision to come here. You heard about it, or maybe your friend dragged you here, or maybe you organized it so you were obliged to be here, or perhaps you were threatened at gunpoint. But whatever the case, you are here. You made a decision to come here. You may not know why you made that decision. Maybe that no one can know why you made that decision, but you considered for perhaps a little while, perhaps a really long time. At some point, a decision occurred, and you are here. I'm inferring this because you're sitting here. Unless you arrived like unconscious on a stretcher, or you're just waking up and wondering what all these people are doing here right now, you decided to be here. Thank you. So I want to talk about why we are here. And I'm talking about literally why are we here. I'm curious, just to do a quick poll before I even begin, how many of you think that free will exists? Surprisingly large number of hands. How many of you think that it doesn't exist? All right. Now I'm curious, how many of you think a definition for free will exists? Because I think this has a lot to do with whether or not you think free will exists. Not very many people think that you can define free will. Well, hopefully we will address that later today. Does anybody have any ideas or thoughts for, like, can you just shout out, like, what does free will mean? Be able to act in accordance with your desires. Anything else? No one else has any ideas for what free will might mean?
You can act without any other force upon you.
All right, you can act without any other force upon you. Those are kind of the basic ideas I think that people think about, right? Free will has to do with also, I think, responsibility for your actions, being able to take responsibility for your actions, that they came from you and not from somebody else forcing you to do them or something else forcing you to do them. Which is why we care about free will, because like the justice system relies on being able to hold people culpable. And if there is no free will, then maybe you can't hold people culpable for their actions. Anyway, we're going to talk about free will, but first I need to say that I am not an expert in most of what I'm talking about tonight. I draw stick figures for a living. I happen to have a degree in theoretical physics, so the parts about physics that we're going to talk about I know more about, but I'm also going to be talking about a lot of other things that are outside of physics. That's just the disclaimer. There's kind of, the reason I think people care about free will is because it seems like a paradox, right? We seem to be able to take action of our own accord and do decisions, whether good or bad things. I don't recommend this decision, at least not from that close. Get your friend to be that person and you can watch from a distance. But the paradox is that it seems like either an all-powerful, all-knowing deity, if you believe in God, or a deterministic physical universe, if you believe in science, those things both seem to suggest that free will should be impossible. So we have a feeling that we experience this thing, which is that we can make our own decisions, and then whatever you believe, it seems like maybe it's not actually possible. So if you take those two things together, you end up with 4 possibilities. One is that you think either you think free will doesn't exist or you think free will exists. And then either you think the universe is deterministic or you think the universe isn't deterministic. And there's some, philosophers have different names for each of the things in these boxes, and that have to do with liberalism and all sorts of fancy words. I think that I'm just going to throw up some random words that I think fit these categories better than the philosophers. But it turns out that science actually does have something to say about this. Science is not going to be quiet. So on the subject of maybe free will doesn't exist, biology and neuroscience certainly have something to say, which I will be talking about briefly. On the area that it may exist, I think computer science actually has some really compelling reasons to think that free will might actually exist. And then physics really just has to do with the universe, whether it's deterministic or not. Physics is not going to address the other part of that as much. But before we get much farther, I think we need to just get a little bit of something out of the way, which is a gross oversimplification, but basically the way that religion deals with this issue of free will and you being able to act of your own accord, even though there's this all-powerful, all-knowing being and deity, is the soul. The soul can somehow exist outside of your physical being and yet still influence it in some fashion. I don't know how this enables you to have free will. God, I guess, doesn't see souls, but sees atoms and electrons or something. But that's the idea. You could also take the Greek or Roman approach of just having gods basically be people with superpowers, in which case they don't know everything and you're all right. But let's start a little bit with neuroscience, since that's the first thing I mentioned. This is not a brain, this is a maze. But neuroscience has some things to say about free will, namely that decisions happen in the brain. And that may not seem like a surprising thing, but there's a lot of research that shows that your unconscious brain actually makes decisions before your conscious brain is aware of them. There have been studies where people are asked to press a red button at a random time or with a certain hand, their left hand or their right hand, and the researchers are monitoring their brains with electrodes or fMRI or something, and the researchers can see when the people decide to press the button sooner than the people are aware of deciding to have pressed the button, and the researchers can thus predict. So this makes us question, is free will, if we can tell based on your brain, looking at it, before you even know what you're doing or what you're going to do. But then you can ask, well, who are we? Are we just our conscious brain, or is our conscious brain just the part of our brain that looks at what the rest of the brain is doing? And of course, if that's the case, then it's always going to be behind the times because it's just watching what everybody else is doing. And I personally think that I am my entire brain and body and not just the conscious part of the brain that may be a little bit late to the party some of the time. So the other thing that neuroscience seems to be telling us is that all of the things that brains do can be explained at some level by physics. What I mean by that is that brains are made up of cells, and cells are made up of molecules, and molecules are made up of atoms and protons and electrons, which are governed by the laws of physics. So, in principle, everything that we're talking about here in neuroscience comes down to some aspect of physics. So, let's talk first about Newtonian physics, which is deterministic. This is the traditional, F equals ma physics, or if you want to rewrite that, basically it says that the position of an object is dependent on, the position of an object going through time is dependent just on the forces that are on it in some way. And so you can basically, if you know where the particles are, where they're going, and what their mass is, you can put this into this machine that has some equations, and it will jump out at you with a prediction of the future. And if you get these numbers in the beginning really, really accurate, then the prediction should be very, very accurate. I'm not going to talk about chaos here because I think that's a different story. But that is the case. So for example, if you have a planet and a moon, and you know their masses, and you know how far apart they are from each other, and you know their relative velocity, you can predict where they're going to go. And we do this all the time. This is how we know when asteroids almost hit the Earth and where the planets are going to be and why certain comets are going to be passing through at certain times. So it's not that hard to imagine that maybe there is like a trajectory for the brain that you could in principle calculate from basic physics. And I don't mean like a physical trajectory as to where it's moving, but actually knowing what it's going to think next and do. And in principle, deterministic Newtonian physics, if you have enough information, you can predict perfectly out arbitrarily far into the future, what is going to happen with all the particles. However, the universe is not governed by Newtonian physics. You may have heard of this development called quantum physics, which happened in the last century. And a lot of people trot out quantum physics as the savior of free will because they say quantum physics is random. It has these weird fluctuations and things happen that are unexpected. But actually, quantum physics is deterministic, with a little asterisk. But people think of quantum physics as being random, but actually it's the same set. It's in a set of equations. This is the Schrödinger equation. But you do the same thing. You start with an initial condition. This is your wave function you start with. You put it into the equation, and out the other side pops what your prediction is for what's going to happen in 10 minutes or 10 seconds or 10 nanoseconds. And so quantum physics is similarly deterministic in this part of it. There is that one little asterisk I talked about, which is the measurement problem, which is basically that quantum physics doesn't tell you what is going to happen. It tells you what's going to happen to this wave function-y thing that describes your particle, but that wave function-y thing isn't where the particle is. It's just kind of some example of where the particle may be and tells you with certain probabilities where you're going to find it. So for example, if an electron goes through the two slits, like the famous double slit experiment, you don't actually know which slit it's going to go through. It also sometimes goes through both, but if you looked at any one of the slits, you would sometimes see it there and sometimes not, and you can't tell. Like the theory just tells you that half the time it'll go through one or half the time through the other, and in fact the theory tells you that it's going to go with some probability in all sorts of places, which is essentially, we can have this graph that says where are we likely to find an electron or a proton or any other particle, and where the graph is high is where you're likely to find it. But that doesn't tell you where you're actually going to find it at any particular point in time. So you might find it where you're most likely to find it, or where you're slightly less likely to find it. It's also possible that you'd find it where you're not very likely to find it, as long as there is a chance of finding it there. And any one, if you do an experiment 100,000 times, you're going to see this distribution, that most of the time, your particle is going to end up in one place that you expect it. But any one run of the experiment, it might end up somewhere where it was unexpected. And we do not know how this happens. That is one of the biggest mysteries of physics and of science, is that we don't know how you go from this description where you say the probability of the particle being here is this much and being here is this much. How does it decide which one it's actually going to end up at when you do a measurement? Because that's how quantum physics works. And we don't know the answer. There are various proposals as to how it might work. One of them is called the many-world interpretation, which basically says that at any juncture where you have multiple possibilities, the universe actually kind of splits, and you have all of the possibilities happen in parallel in this ever growing, crazy, bigger version of the universe. And we just happen to be experiencing life along one of these paths. So, you might say the electron could be here or here, but we only see it showing up here because we only follow one of these paths. I kind of think this is just kicking the can down the road, because you still then don't know why we are following a particular path. And so there's still this open question that the step where you actually decide which of these things is going to happen, we don't know how that happens at all. There are lots of physical theories and models that have been proposed to explain how it happens, but none of them have been actually able to be tested or separated from each other. So it could actually be that it is just random, that there is nothing more subtle or sophisticated underlying it, that it is just complete randomness. But I'm not sure that randomness actually is that good for free will, because if randomness is all it is, then you might have to say, well, coins have free will and electrons have free will, because if something occurs randomly, if that is where your free will comes from, then there's nothing different between you and a coin. So quantum mechanics, just by being random, doesn't necessarily save things either. There is, however, space for other things. I'm going to call them souls, because a lot of people kind of call free will and the soul as the same thing, and something that kind of can exist slightly outside or separate from physical reality yet still influence it. And so I'm going to talk about where souls can fit into physics, or also other supernatural phenomenon. The space is very small, and it is getting smaller every day. Hundreds or thousands of years ago, there were a lot of things that you could explain by supernatural means because we didn't know how they worked. Now we know how they work, so we don't say that the gods will the planets to move and carry the sun across the sky. We know that that works in a different way. So there's less space for God. It's getting smaller and smaller, less space for souls. But there still is space. One of the places where there is space for more God than souls is in the actual initial conditions and the physical laws. So we don't know why the universe started off in the state it did. It just did. We don't know why the laws of physics are what they are. We know what they are, but we don't know why. And so you could say, well, maybe there was some supreme being that said, okay, this is the laws of physics that we're going to have in this universe, and this is how we're going to start it. The same way that often that people who are doing experiments get to say what the setup of the experiment is. You could imagine that. Now, there are physicists who are working on creating models for the universe that are self-consistent so that the model actually explains itself, and then you wouldn't have need for this anymore. But those are still works in progress. One of them is this kind of evolutionary model with black holes and things, which we can get into if people are curious about that later. But basically, this is still an open place where we don't know, basically, how the universe got to the initial conditions it did and why the laws of physics are what they are. Another place is quantum measurement, which is what I talked about before, which is this idea that quantum predictions just tell you the likelihoods of what things are going to happen. They don't tell you actually which one of the options is going to happen. And so it is possible that on any given one result, some soul particle thing could interact with the electron and say, okay, this time you're going to go that way, or this time you're going to go that way. And in the grand scheme of things, if you just tweak one or two of those every once in a while, no one can notice because the only way we actually notice these patterns is through statistical ensembles. So you can actually, it's like if you're flipping a bunch of coins, you could just flip 100 coins, and one in the middle you could say, okay, that one's going to be heads. And if you looked at that afterwards, it would be really hard to tell that one that you said was heads wasn't random, that it was actually you who said it that way, because there's 100 coins, and you're just looking at this random assortment of things. But random things have to look random, and I want to give an example of this and how hard it is and how constrained it is to actually to create and mess with random things and have them be random. So here is a string of bits of numbers, zeros and ones, and I'm curious, does this look random to you? What do you think? People are shaking their heads probably because they think that I'm setting you up. Let's get a poll. Raise your hand if you think it's random. Raise your hand if you think it's not random. Raise your hand if you didn't vote in the first two votes. That's a good sampling of the population. So one of the things about a random sequence of numbers is that it has to have on average, over really, really large numbers of this, you should have about an equal number of zeros and ones. This is actually quite a short string. This is only like 30-something digits, and so you really need like thousands and tens of thousands to see some of these statistics bear out. But you should have an equal number of zeros and ones if it is truly random. In addition, you should have an equal number of pairs of 0 zeros, 0 ones, 1 zeros, and 1 ones next to each other. You should also have an equal number of 0 0 zeros, 0 0 ones, 0 1 zeros, right? Like all these possible strings, if you look up there and pick any one of those strings and count how many there are, you should have an equal number of them. It means you should also have an equal number of, 10 zeros in a row you should have in the same frequency as you have 0 1 0 1 0 1 1 1, whatever it is. And so you can actually do this analysis, and you can look at all of these things if you have a string of numbers and say, well, do these things actually look like they're random or not by looking at the frequency of all of these patterns. It's not just that you have the same number of zeros and ones. You should have the same number of all the kind of possibilities for any length sequence of numbers. So I counted this one here. Turns out that there are 18 zeros and 18 ones. So that looks good. As for the 0 zeros, 0 ones, 1 zeros, and 1 ones, there's some slight variation, but it seems to be mainly around like 8 or 9. So it's hard to see any variation there. But when you get to the longer ones, you can see that the ones that are 3 zeros in a row or 3 ones in a row didn't get very many as opposed to some of the other ones. That is not anything, it's possible that this string of numbers, random string of numbers, could generate that. that distribution of all the zeros and all the ones. But that's a good indication. This right here, the 0, 0, 0, and the 1, 1, 1, that those are so low, that there are so few of those. It's a good indication that this string of numbers was come up with by a human. Because we look at long strings of zeros or long strings of ones and say, that can't be random, that's too many ones in a row. Let's add some zeros in there. And it turns out that indeed, I just made this string up, that it is not random. Well, it was random by me, but clearly I'm not a good random number generator. If you find, you can find random strings at the website random.org, which uses atmospheric noise to generate random strings of numbers. This one has a very different distribution of these things. To start with, it actually has way more zeros than ones, which kind of messes up all the other statistics later on. But like a person generating a random string of zeros and ones would probably never put this many zeros compared to ones. We would try to make it even. And then you have things like there are a lot of 0, 0, zeros, but there are very few like 0, 1, 1s and 1, 1, zeros. And these two actually were the ones that were the most in my sequence that I made up. So random numbers are very actually constrained when you have a lot of them. You can see in here there are some really long strings of ones and zeros in various places, because that's what randomness has. So my whole point of this is that if you're going to go in and mess with these things, if a soul or a god or anybody is going to go in and say, okay, this electron is actually going to end up spin up this time or spin down that time, or go one way or another, or interact or not interact, or some radioactive material is going to decay now versus in 10 seconds. You could flip any one of these zeros to a 1 or ones to a 0, and no one is going to notice. But if you do it enough, to change the world probably, and they actually change the outcome of things, you're really going to be constrained as to how you can change it without making this sequence look non-random. And whenever we look at elementary particles doing these sorts of things, it looks pretty random under all these ways. So there's not a huge amount of room. And in physics, at least, it doesn't seem like there's a whole lot of other places other than initial conditions, laws of physics, and quantum measurement that you could actually have some sort of supernatural thing that's kind of like in a different plane from our universe that's poking in and influencing things. And this is because people do studies and they do research and they do X-rays of the brain and fMRI and other sorts of things, and you see that the reason MRI works is because all those electrons are behaving the way we think electrons behave, and all the nuclei. There's all sorts of things in the brains. When you do positron emissions scanning and that sort of thing, you have physics behaving the way you expect it to behave in somebody's brain or in other physical objects. And so there's really not a lot of space left in physics for things, for these larger and more kind of supernatural influences. So then there is this question of histories, going back to the many worlds and the measurement idea, that I said we follow, if the many worlds picture, if you think about the many worlds picture, it would suggest that we would follow one possible path among all the possible histories the universe could have. And free will often asks, one way people often come to define free will is the idea is like, if I went back in time and redid things, could I go in a different path, in a do-over, right? If you went back and did it again, do you have the freedom to have made a different choice? That's one thing that people always, it's a kind of a mental exercise people very frequently do when they're thinking about free will, is to say, I made that decision yesterday. If I went back to right before the decision, could I have made a different decision? And I think that physics really says that that's not a good way of thinking about electrons and smaller things. But we can't go back in time to yesterday and put all of the atoms in your body in the exact same configuration they were in yesterday, along with the room and all the molecules in the air. Like, we can't redo that. And so you can't actually ever have a chance to redo your thought process or decision process. So we don't actually have a way of falsifying that experiment. Really, what we can do is we can say, how do your decisions happen? Can we predict them? That's really what free will is about. It's, can we predict what you're going to do? Because that's the only thing we can do, is we can say beforehand, this is what you're going to do. Because you don't get do-overs. There are no do-overs in life in this sense, that you can't actually go back in time. So as soon as we start talking about being able to predict the outcome of decisions. And if you think about brains as being made up of physical particles that interact and obey the laws of physics, according to some sort of physical laws, some kind of an algorithmic way, it brings us to computer science. And I think computer science has some of the most interesting things to say about free will, in particular because computer science, which I love, is very much more about what is possible in practice rather than what's possible in theory. So the universe is big, and you can imagine that maybe there's a lot of stuff that you could do with it, especially if you have infinite space and infinite time. But computer science kind of says, well, what if you're actually going to do things in some sort of organized way, have some sort of algorithm and try to actually do a computation or a calculation, and how much can you actually do with that? Because it turns out you're actually much more constrained by algorithms than you are by maybe what you think the universe could do. So the reason that we can talk about this at all is that brains can probably be simulated on computers, in principle. I don't think people are doing this yet, but this could happen in two ways. One is directly, because we know that brains are made up of neurons and there's neural networks, and if you can figure out how neurons interact, you could simulate that. Basically, you could create digital neurons and they could interact in a certain way. You could maybe, if you knew somebody's state of their brain, you could run it forward and predict what the brain is going to do in 10 minutes. The other way you can simulate brains is the really hardcore way, which is via physics, which is that we know brains are made out of physics. So if you just simulate all the physics all at once, without even knowing anything about how the brain actually works, you should be able to get the same answer. Now, neither of these are possible yet. The one on the right is possible kind of in principle right now because we know how the physics works, but we're never ever going to be able to have a computer that's good enough to do that because we can't even do computer simulations of full quantum mechanical computer simulations of large numbers of atoms, like in the hundreds and thousands. So being able to do a brain is way, way in the future. This is probably the much more likely way to be able to simulate a brain, which at this point I don't think we know enough about actually how brains function to be able to, and also about how to actually scan a brain to input its initial state. But this one is the one that I would say we're actually could do that in the near future. The right side is a crazy idea. So when we're talking about computers, we need to talk about something called Turing machines. Is anybody familiar with this concept? Raise your hand if you've heard of a Turing machine. Surprising number of people. Well, I will go quickly then through what a Turing machine is. It's basically a simple abstract computer. It's kind of like a idealized version of a computer. I'm going to talk about Turing machines in terms of light bulbs that you can turn on or off. And you're standing in front of a light bulb, and there's actually an infinite number of light bulbs in a big line, left and right, but you're standing in front of one of them. And a Turing machine is basically just you following instructions. So you have a card in front of you. You have a stack of cards, actually, but this is the one that happens to be on the top of the stack, and it says some instructions about what to do if the light bulb is on or off. So if the light bulb's off, this card says, then turn it on, go to the next light bulb to the right, and then go to the second card. And there's some instructions for what to do if the light bulb were on, but it's off, so we'll ignore those. So we'll do this. We'll turn the light bulb on, go to the right, and then go to the next card. And this card has some instructions too, which says if the light bulb's off, then we'll leave it off. We'll go one light bulb to the right and go back to the first card. So now we're at the first card, which says if the light bulb is off, we'll turn it on, go to the right, go to the second card. And now the light bulb is off, so we'll leave it off, go to the right, to the first card. You can quickly see where this is going. This is just going to turn on every other light bulb and never stop. It's going to go off forever. If we have infinitely many light bulbs, it's going to keep going and going and going, because it only ever goes to the right. But maybe if we go back, we can find a more interesting program. If we go back to the very first step here, or the second step, where the problem was, the point where it got boring was when we said go right again. So you're always going right to light bulbs that are off. Let's change that. Let's make the second operation turn on the light bulb and then go left and go back to the other card. So now let's see what's going to happen. I'm just going to blindly follow these instructions. Turn that light bulb on, go back to the left. Oh no, we have a new thing to do because this one is on now. So if it's on, then we leave it on and go to the left and go back to the second card. So we'll do that. Now we're on the second card. It says if it's off, then turn it on, go to the left, go to the first card. So we will turn it on, go to the left. Now we're at the first card, which says if it's off, turn it on and go to the right. So now we're going to go to the right, go to the second card. Now the second card says if it's on, we stop. We have completed our program. It successfully turned on 4 light bulbs and then stopped. So it's not running forever. And this is very different from the first program, because the first program just kind of like, it's like your computer just looping, never ending. Whereas this one actually got something done. It turned on 4 light bulbs. Now you may be asking, why do we care about all these light bulbs and turning them on and off? It happens to be that Turing machines are universal computers, or can be used to program a universal computer, which means that in principle, you could run like Windows by turning on and off light bulbs if you had a long enough string of light bulbs and a large enough stack of cards and enough patience. In practice, we normally turn the light bulbs into 1s and 0s, and then our card is just telling us what to do with some 1s and 0s, and we have a larger stack of cards. But you don't actually need that many cards. You need 15 cards, and there's a specific set of instructions for them. 15 cards is all you need to create a universal Turing machine, which can simulate any other computer in the universe that would be able to compute anything. The input for that computer is, instead of starting with all 0s or all lights off in the line, you'll start with some of them on and some of them off, and that's kind of your initial state, your initial data. This is the list of what you should write on those cards if you want to make a universal Turing machine. It's just right there. It's in a slightly different notation. Instead of 1s and 0s, it's C's and B's. But for example, this one says the state, first card, U1 is the first card. If you start with a C, which is like a 0, I guess, move to the right, or leave it as a C, move to the right, and then go to the second card, etc. So take a picture of that, because that's how you can simulate Windows on light bulbs. You may have noticed, though, that one of the interesting things about the 2-card Turing machine we did was that one of them just went on forever and the other one stopped. And this is a very important question, it turns out, for computers, if you want them to do anything, is you need to know, is it going to stop? Does it halt? I don't know why it's called halting rather than stopping, but it is. And there's a question is, can you tell, just by looking at the source code, or just by looking at the cards and the input, without actually running the program, can you tell if it's going to stop? Because that would be useful to know. Like if a computer program is going to run forever, you don't want to run it. You want to just say, OK, let's screw that one. Let's go to the next one. Unfortunately, there is no way of doing this universally. So this was proved by Alan Turing, after whom Turing machines are named, that any algorithm, any way you have of checking programs just by looking at their code or whatever to see if they're going to stop, it can't give you an answer for all programs. There's always going to be programs that you don't know whether or not they're going to stop or just keep going forever. And so basically this means that sometimes you just have to run the program and see what happens. This is kind of akin to having like a kryptonite for the halt checking algorithm. So you have an algorithm that checks if programs are going to stop or keep going. There are some programs that it can't tell you anything about without just running them. Now, I'm going to try to give you some examples of why it's actually really hard to tell if programs are going to stop or not. Because the ones that we saw, it was really easy to tell with the first set of cards. It was just always going to go to the right and it was never going to stop. So sometimes it's easy, but sometimes it's harder. And this is basically saying that for arbitrary programs, you can never actually just look at them all and be able to tell. For the same algorithm will never be able to tell for all programs whether or not they will eventually stop. So to give an example of why this might be really hard, I'm going to talk about something called Busy Beaver programs, which is a Busy Beaver program is basically a program, which is basically the set of cards, that will run for the longest amount of time, but then stop eventually. So basically, you want to find the program that will go and do a lot of stuff, but still stop. And the reason that this is interesting, and the question of how long it can run is interesting, is because this is basically the boundary between programs that halt and programs that go forever. So if you could know that all programs either halt after 15 steps or they go on forever, then once a program gets to 16 steps, you know it's going to run forever and you just ignore it. So it's useful. And we actually have seen an example of a Busy Beaver program. One of the 2 examples we showed before was the Busy Beaver. So this program here, which was the second thing we did, it goes to the right, then it goes to the left, turns on 4 lights, takes 6 steps, and then it stops. So that is the busy beaver for when you have 2 cards. You can turn on at most 4 lights, and you can take at most 6 steps. So I'm going to just go through really quickly through these programs. Basically, if you have, for example, 1 card, there are enough options on that card with whether you turn the lights on or off, and whether you go to the left or right, and what card you go to next, to have 64 possible Turing machines, which seems like a lot for 1 card. But the busy beaver only goes 1 step, because you only have 1 card, so if it goes to the right, it's going to keep on going to the right and go forever, so you need to stop on the first step. And it can only turn on 1 light. The 2-card busy beaver, which is the one that I just showed you, well, there were like 20,000 different possible machines we could have made, but the one that I showed you out of those 20,000 goes for 6 steps, 6 operations, and it turns on 4 lights. The 3-card busy beaver, there's a lot of possible Turing machines. This is not the number of busy beavers, this is just the number of possible machines you have to look through to actually check what the busiest one is. Stops after 21 steps, and it turns on 6 lights. So essentially what this is saying is that if you have a 3-card Turing machine, that if it runs for more than 21 steps, it's never going to stop, ever. Which is useful if you're using a 3-card Turing machine, which is, I don't know what you can do with that. If you have 4, the numbers get a lot bigger. There are a lot more possible machines. Still only 107 steps it can do, and only turn on 13 light bulbs. And then when we get to 5, there's maybe another 3,000 times as many machines. And we don't know how many steps the program goes before it stops, what the longest one is. And we don't know how many lights it could turn on. We have some lower bounds. We know that there is a program which goes for 47 million steps and then stops. I don't want to do that on my light bulbs. And that program turns on 4,000 of the light bulbs. But we don't know if that's the biggest, if that is the boundary between stopping or going forever, because there are still 40 programs that have 5 cards, 40 known programs that we have let run as long as we can let them run, and they have never stopped, but we can't prove that they're going to go on forever. We don't know. Maybe they'll go on a lot longer and then stop. It seems like this is probably the answer based on what we've looked at, but we don't know. So this is how hard this problem is, that already after you only have 5 cards, you can't know the answer, or we don't yet. And this number, I think, one of these numbers was found, actually that number was found in the 80s. For 6 cards, it's even more crazy. It's like 10 with 30,000 zeros after it is the number of steps that we have. We know that there is a program that goes on for that long and then stops, which is insane. And that's just the bare minimum for this. So that's just for 6 cards. Now, I think you may recall that I said that you need 15 cards for universal computation. Now, of course, these calculations were made based on using a certain number of cards and just all zeros as input. In order to do universal computation, you start with 15 cards that you know, and you change the inputs. But it still gives you an idea of, like, it's really, really hard to know if a program is going to stop at some point or if it's going to go on forever. And this is something that the halting problem, basically, this is kind of like both and gives you an emotional feeling for how hard that problem is, but also it's essentially a consequence of that problem. So I think what this kind of says, is, as I've said, determinism maybe doesn't actually matter that much, because free will wants to know if you can even tell me what I'm going to do. Essentially, if the brain is a computer or running operations, or if you can simulate it on a computer, the question is, can you actually predict what the brain is going to do? If it takes millions or hundreds of millions or like 10 with 30 zeros after 30,000 zeros after it operations to actually predict what a human brain is going to do, and it'd probably take a lot more for a brain because it's a little bit more complicated than a 5-card Turing machine or 6-card Turing machine. That becomes a more practical question. So the point here is that even in a deterministic system, like this Turing machine is just cards that have instructions and they do exactly what they say. It's a totally deterministic system. You still have this case where you might not actually be able to know what the outcome is until it happens, which in some sense to me is maybe what free will, or is one way of thinking about free will, that you don't know what's going to happen until it happens. that that program is the only thing that knows what it's going to do, and it doesn't actually know, it just has to do it. Now, of course, we've been talking about infinitely long programs or infinitely long, strings, and we don't have infinite time. So the question is, can programs or things that decide and make decisions, because any decision you make is essentially a computer program, which is saying, do I have an output yes or no, 0 or 1? Can we know our decisions before we decide, or sort of thing? Basically, is there a shortcut? Is there a way of cheating, even if you have only finite time? So there is a kind of a finite time version of the halting problem, which has to do with if I run a program, but then maybe after a certain amount of time, if I haven't actually come to a solution, it just says, okay, you failed or you stopped. It's kind of like if you're coming to this talk, or if you're trying to decide whether or not to come to this talk, and you take so long deciding that you missed the talk, you've decided not to come to the talk. That sort of decision. And it turns out, you can prove using the halting problem that there's no general technique to determine if a decider will come to a decision. And so even with the imposed time limits, basically what you can then prove is that any way of telling is likely to take longer in terms of the number of steps or computational steps than it takes for the decider just to make the decision. So if you're running a program or trying to make a decision in your mind, it's actually faster for you to just make the decision than to figure out what your decision will be based on the program that you're running. So this applies both when a program is analyzing another program, so if somebody is trying to analyze your brain or analyze a program to see when to stop, but also if you're trying to analyze yourself. So for yourself, this is useful because it basically says just shut up and make your decision rather than trying to figure out how your decision is going to happen. But the main point is that you actually have to go through a decision process. In general, there are decision processes that you don't have to go through that you can look at the code and do. But in general, for arbitrary decisions, you actually have to go through the process to know the results. And I think this is kind of why computers do unexpected things. Right? We think of computers as being these very, the computer does what you tell it to. And that's true, but the computer also is a program that's doing all sorts of crazy things as inputs all the time. Sometimes it seems like computers have free will. And this is also why these progress bars that tell you how long it's going to take, those are total lies. Maybe if they're if it's for copying files, then sure, it knows how long it's going to take because it knows how big the files are. But if it's to figure out how long it's going to be for a program to run, if you're doing a calculation. Sorry, I ran through here. It doesn't know. The computer doesn't know how long it's going to take. The progress bar is just there so that you stop complaining, and so that you know that it's still actually doing something. That's the main thing. But yeah, because the computer can't. The fastest way to know how long in general a program is going to take to run is to run it. So you've all had the experience of the progress bar doing crazy things, going really slow, really fast, and then stopping at the last minute, etc. But the main point of this is that if you had a fast enough computer, you might actually be able to simulate a brain. You could not simulate the brain necessarily, in fewer steps than the brain takes to do its simulation, but the computer can probably be faster than the brain eventually. I think sometime quite in the last several years, maybe even, the fastest computer on the Earth has surpassed the processing power of a human brain. Doesn't necessarily mean that we can run a human brain on that computer yet. We'd probably need a couple of orders of magnitude more power. But computers now are more powerful than brains. So in principle, if you had a computer that was fast enough, you could imagine that the computer could simulate your brain if it knew the initial conditions, and it could do it faster than your brain. So now this question is, what does this mean? What does this mean for free will if the computer can actually, run through your brain's processing or run through the decision? Well, I think there's one wrench in this problem, which is that you don't exist in a vacuum. We exist in a universe that we get inputs from all the time. So while I'm trying to make a decision, maybe my friend shows up and starts talking to me, or maybe I get an email, or a fly lands on my neck and I swat it. There's all these things that can happen that if you're just modeling what's going on in my brain, you're never going to actually, be able to involve those things and take those into account. So if you want to actually correctly use a computer to predict what a person is going to decide, you need to take into account the rest of the universe. You need to simulate the rest of the universe as well, or at least, the room around that person, or at least a sufficiently large, sphere of influence around the person, so that those inputs that happen don't, mess up your simulation. And it's the same way that when your computer is running a process and that process bar is going across, if you start doing other stuff on the computer, you might influence, depends on how the computer architecture is built, but you might influence that program that's running and change its behavior. And so this is why computers are unexpected and do unexpected things. And in some sense, you can argue that computers have free will in this way, in the same way that people do, because computers don't know what they're going to do in advance until they do it. They don't know the outcome of running a program. We don't know the outcome of doing, in general, there are definitely programs that you can run that you know the outcome of, or there are certain decisions that you could probably make that you wouldn't know the outcome of. So, to me, this is where I think free will is the most interesting, because you've started in this place where you said maybe physics is deterministic, or maybe it's not deterministic, maybe physics is probabilistic. Either way, maybe that doesn't have anything to do with free will. Free will is still this problem of how do we arrive at this. There are some holes in physics where you could fit free will in. But to me, what's the most interesting is that even in an entirely deterministic situation, you can still have this notion and feeling of free will. I mean, it has been argued by people that is why we feel that we have free will, is because we don't know what's going to happen until we actually go through the process of thinking out the decision. I find it's actually similar in a creative process as well. You can think about what you're going to do and what you're going to write, or what your talk's going to be like, or what the video is going to be. But then you actually sit down and do it, and it's not until you do that it actually ends up being what it is. You have to go through these actions sometimes. You can't analyze how it's going to happen beforehand without doing it. So yeah, free will involves the brain, obviously. I think computer science has a lot to say about it. Physics has a little bit to say about it. And I'm surprised how quickly I got through that. But now we can have a discussion about it, or if you have any questions about other things as well. So thank you for coming. That was much shorter than expected, but hopefully you have... Well, I guess, I don't know if I should thank you for coming, because maybe you didn't actually decide to come. Maybe you were just destined to be here.
Okay, so now we're going to do a Q&A, and the way we're going to do this is please raise your hand if you have a question, and I will do my best to get everyone. We're going to let out at 8:30, so we have about a half hour. You first.
Thank you so much for the talk. So I was just curious, I recently read stuff about quantum computing. I have no idea how to comprehend that. How does that add to this discussion of free will and the way you've used computer science to understand free will?
Right. Well, quantum computers operate in a different fashion from classical computers, but it's mainly to do with their efficiencies. So they can do calculations and certain kinds of calculations kind of more natively than classical computers. So like a quantum computer can simulate a quantum system very easily. A classical computer can still simulate a quantum system. It just is a lot more work for it to do. So quantum computers, because they're essentially still running on the same laws of physics that you can simulate in a classical computer, it doesn't change any of the kind of actual underlying ideas or proofs here. It will make things more practical to do. It may make the existence of the brain sim 9000 much easier to happen, but it doesn't actually change qualitatively. It's just a quantitative kind of change. Yeah.
Questions?
Hi, thank you for that talk as well. I think a lot of what you talked about kind of equated predictability with free will. But something about a computer, right, and it might not know what it's going to do before it does it. But that doesn't really make me think that it had a decision in what it did in the end, right? And so, like, I wouldn't blame my computer for anything it did wrong. But I might blame a person.
That's where you're wrong. No.
But I might blame a person for doing something, so there's a disconnect there.
Right. Yeah. No, I think you're totally right that we feel like there's a disconnect there. I think there is one issue that free will and consciousness are not necessarily the same thing. That being aware, I think like as I was talking before, there's all these experiments that say our conscious brain is essentially just there watching what the rest of the brain does, and it kind of gets updated later, right? Like it's the person watching from the satellite view when the guys are on the ground doing all the stuff, doing all the action. And there are things that the conscious brain can do, and often it's just to stop actions that are happening from the unconscious brain. But to me, the unconscious brain is me just as much as the conscious brain is. And so I think if the free will part is happening in the unconscious brain, then to me that's not really any different than a computer. The computer doesn't have the consciousness part yet, maybe just because we haven't really designed computers to look at themselves all the time. But there are, you can write computer programs that monitor what the computer's doing. And there are things like Activity Monitor, which will tell you what the computer is doing, and they can look at themselves, and they can have kind of the computer's version of self-reflection. I do think that we have a psychological, obviously a difference of opinion, basically, or feeling that somehow what people do they're responsible for, whereas what the computer does, I don't know, probably people who made the computer are responsible for. But the main difference in that, I would think, is not really a difference between holding, it's not a difference in how that the computer itself is responsible for what it does, or my brain is responsible for what it does. Like the computer is responsible for the operations that it runs and what results it gets. Like those all come from the computer. The only difference is that a person, like no one made the person, whereas somebody made the computer and designed it. So if the computer does something bad, you can then point at a person who's behind it. Whereas if a person does something bad, we don't have anything beyond that person to point at, which is why I think that's why we stop and think that people are responsible for people actions, whereas computers we don't hold responsible. But I think it is possible that in the future we might start holding computers responsible. So computers as soon as computers start programming computers and designing computers to a large extent, I mean, they already can do that, but as soon as that happens to a large extent and computers can kind of update themselves and update their own operating systems, I think that we will have to start holding computers responsible for their actions. And if you start having a computer, I mean, the easy thing with a computer is just turn it off, right? That's a little bit of a bigger decision with the person.
If you guys could please stand up when you ask your questions, that would help a lot. Thanks.
Question about your university. Would you recommend its graduate program and also undergraduate program, and are you Canadian?
All right. You're talking about the Perimeter Institute?
Yeah.
All right. So I am not Canadian. I'm Minnesotan, which is close. The Perimeter Institute, Perimeter Scholars International graduate program is excellent. It's really, really good. It's very much disconnected from the University of Waterloo. Waterloo has a good physics program, very good physics program, very good math program. Those are kind of the two. I mean, it's also very good in engineering, but physics and math are things that it's very well known for. But the Perimeter Institute is an institute it's affiliated with the university, but it's separate. So the master's program there is great. It takes a really interesting approach to teaching physics, which is that basically they give you kind of a crash course overview of everything that's done in modern physics, rather than starting you off with kind of the traditional approach of learning electromagnetism, learning quantum mechanics, and only like after year 2 or 3 of your PhD do you actually like start to learn about current science, and then maybe it's too late for you to switch fields. I think the Perimeter Institute Perimeter Scholars Program is great because it exposes you to a variety of fields early on. Other fields of science don't have this problem. Physics does, because you have to learn so much often before you actually get to anything that's being currently done. But yeah, I would highly recommend that program. I don't know anything that much about the undergrad program, though.
Question?
somehow in aggregate they become non-deterministic, and it seems to me kind of like an argument from we can't realistically figure this out, and therefore free will. It kind of seems like jumping to the result.
So I'm not saying that at any point it becomes non-deterministic. It's deterministic all the way throughout. I think what this kind of argument is arguing for, and I'm not sure how much I buy into it either, but I think it is really interesting to think about, is the idea that maybe that is where the feeling of free will comes from, even if we, that may be, and that it almost may be equivalent to what we really mean by free will, that you cannot know in advance what's going to happen. Because I think when you actually come down to it, defining what free will is, depending on exactly what you say your definition is, it changes a lot. If I say my definition for free will is being able to predict in advance what somebody will do, or that's like an argument against free will, right? If I can tell you what you're going to do, that means you don't really have free will. So that becomes, to me, that's the only kind of operational way you can talk about free will, because you can't do I'm going to go back in time and do a decision in a different way. That's not possible. So my personal view is that the only way you can actually talk about free will has to do with how do we make decisions? Can those decisions be predicted in advance? And the question then is not can they be? I mean, it is can they be predicted in principle? And the halting problem says no. So it's not, and it is kind of maybe this crazy jump. And the point is that there are definitely lots of programs or lots of things your brain might be doing that you can very easily tell in advance what's going to happen, but there are always some things which like these busy beaver problems, which are so insane that you will not actually be able to tell in advance what's going to happen. And then I think the kicker is when you actually add in the fact that there's continuing input from the rest of the universe, right? Because a computer could simulate a brain faster than the brain can run a busy beaver problem, for example. But as soon as you have all these other crazy inputs coming in from the fact that I'm looking at people out here and how do I decide who showed up, why is somebody's wearing a red shirt there and they're not wearing a red shirt over here, those things influence me, and you have to not only simulate my brain, but you have to simulate all of those things, which includes a lot of other brains.
Hi, so thank you for your talk. It's very insightful. Also, I was wondering, you mentioned that there's something in the works about physical models modeling themselves or something like that.
Yes.
In physics, I don't know. It's a ghost in my head right now. But you mentioned something about that. Could you elaborate?
Right. Yeah. So one of the biggest problems in cosmology, it depends on who you ask, but a very big problem in cosmology is the fact that all cosmological theories, it's a very foundational problem that all models of cosmology or of physics basically follow this paradigm of here are the physical laws, here are the initial conditions. You plug the initial conditions into the laws, which are mathematical equations, and it tells you what happens. And that can explain, if you get those laws right and the initial conditions right, that can explain everything that happens afterwards. But that paradigm can never explain why those laws are what they are or why the initial conditions are what they are. And so I know people in the field of theoretical physics and cosmology who basically are interested in the ideas, is it even possible to come up with a theory that does explain itself in some way? It often seems like you just kick the can down the road another step. You'll add something else that explains why the laws are the way they are, but then why is that the way the universe works? And so there's this question of, can you devise models that at least have more of a sense of, in physics there's this thing called the fine-tuning problem, which is the fact that a lot of the fundamental physical constants, like the strengths of gravity and electromagnetism and various other interaction constants, and also like the values of the cosmological constant, all of these things a lot of them are values that seem arbitrarily unlikely, and it's like it just happens to be everything aligned so perfectly for our universe to exist. And if the numbers were slightly different, then you'd have just mush everywhere, or you wouldn't have galaxies or stars or planets. In kind of the same way that people used to argue that everything on Earth was so perfect for life to arise and so unlikely. And the question is why was that the case? And in a place like Earth, you could maybe use the anthropic principle, but for the entire universe, we don't know that there are about other universes. But there are models. One of the models that's kind of like the simple toy model is called this. It's like the evolutionary black hole model, where the idea is that black holes aren't just singularities. That inside every black hole basically is an entirely new baby universe, and that universes basically have offspring by having lots of black holes. And so the more black holes the universe has, the more offspring it has. And so you have this kind of evolutionary selection to basically end up with universes that have lots of black holes. And it turns out that if you have the conditions to have lots of black holes, you also have the conditions for stars and galaxies and life. So that is one example of kind of, I don't think anybody takes that seriously, but it's an example of a kind of model that basically at least tries to explain why some of those initial values are the way they are. There's still kind of this question of maybe like why does the universe follow mathematical rules in the first place? There are a lot of questions for which it's turtles all the way down.
Hello, Henry. Thank you very much for traveling all the way over here to see us. What point in your career or in your life do you become interested in the topic of free will to the point where you're able to come and give a speech to us now?
Not actually that long ago. Probably a couple years ago. I mean, I obviously have the scientific background for the physics and a lot of some of the computer science. The computer science stuff I just learned because I think it's cool, and the physics stuff because that was what I studied. But a couple years ago, I had some arguments with discussions with some other YouTube video makers about free will, and we were all together at a conference and had this kind of poll as to who thought free will existed and who thought it didn't. And so we had arguments about what we meant by free will, and I had this feeling, at that point I had this weird intuition that I thought, like, even if the universe is deterministic, that maybe there's some way that you could still have things that have this sense of freedom of will. It just seemed like I couldn't rule that out, that you would have the perceived, because I am aware of things like chaos theory where like small perturbations to initial conditions lead to vastly different scenarios. It just seemed to me like just by saying the fundamental laws are a certain way doesn't mean that the emergent phenomena have to be that exact same way. And so I was very pleased to discover papers talking about relevance of the halting problem, for example, to free will. I thought that was pretty interesting. So yeah, just a couple years ago, but I've on and off have read a lot about it, and it comes up. A lot of these things come up in, like, I've taken things from other stuff I've read that weren't about free will, but maybe more about souls or God or things like that, and try to kind of piece them all together.
I got pumped when you started talking about computer science because it's my major. But my question is, there's this idea in computer science where to explain a system of a certain complexity, you need at least a system of that complexity to at least model it. And I was wondering if this idea, because it seems like the numbers that you were throwing out there makes free will, even to imagine modeling it to the point where the numbers are too big and you can't. I was wondering if that is part of what you're getting at, and if that is it kind of futile to even try to set up a system, I guess, to
right.
understand it?
That is kind of the point. I mean, that is essentially one of the things that is interesting about the Busy Beaver program is that the sequence, the sequence of numbers, which is like this number of steps it takes for that sequence for the Busy Beaver problem to halt, that number that went like 6 and then 13 and 27 or something, 107 and then like 47 million, and then something times 10 to the 30,000, and the next one is like astronomically bigger. That sequence is so grows so quickly. It's like it is. In computer science is called an uncomputable sequence because there is no way of actually, it grows so fast that a computer can't actually compute the next value of the sequence based on a specific algorithm. The only way you can know what the next value of the sequence is by trying out all the Turing machines. As to the question of whether it's a futile effort, I do think that kind of it is maybe a futile effort to eventually simulate like the entire universe plus all the brains to figure out what this one brain is going to do because of all the input. But at the same time, I think that there are certain things that humans are actually quite simple in many ways, and we can already make lots of predictions about the ways that people act in certain scenarios because our brains are hardwired to do certain things. And so those are kind of like the simple programs, like the one that just goes to the right forever and turns on every other light bulb. Those sorts of things we do have the ability to simulate, and once we know a little bit more about the way that neural networks work, and we're able to simulate kind of basic operations of the brain, because the brain works by kind of just signaling between neurons, is essentially the way we understand it to work. So I think what I'm trying to say is like that there's a very practical sense where we'll be able to actually kind of make a lot of predictions about certain kinds of decisions or certain kinds of actions that people will take. But there will always, what the halting problem basically says is there will always be certain decisions for which we can't make that prediction. And I think that to me is where there is like this glimmer of hope for the idea of free will, because it's those ones which are saying, you can't predict everything. You can predict 99.9% of the things, but if you can't predict that 0.01 or 0.1 or whatever it is, that's where there is still this freedom.
You noted one problem in discussing free will is that you can't go back in time to see if you would have made the same decision. And one scenario in which you could do that is virtual reality simulations, like a game. By loading a previous checkpoint, you could get in exactly the same state as you were before. And you could simulate non-determinism by pseudo-random generators, for example. And it could be argued that our reality is also a simulation, right? And you can't prove otherwise, for example.
Right.
So can we say that the problem of free will is in a sense undecidable, like the halting problem?
I don't really know. I do think that the fact that you've related the idea of simulations in video games to the fact that our reality may be a simulation is, for me at least, that is arguments towards viewing free will, if you think it exists in this sense, to be valid for computers or for simulations run on computers as much as it is for human beings or any other sufficiently complex algorithm. As to whether or not the halting problem tells you that you can't solve this particular, I'm inclined to say no, because the halting problem isn't about any specific one program. It just says that there are going to be some programs that you can't calculate whether or not they're going to stop, but you don't know which ones those are. So if you're given a specific problem, you can look at it long enough to figure it out, right? That's what these Busy Beaver ones, like there's 40 left for the 5-card Busy Beaver that are still running, essentially, that we don't know, but we're looking at them, and eventually we'll figure that out. The halting problem just says that in general, for a particular algorithm, we won't be able to know, but we're going to try a bunch of different algorithms on those programs. And so that's where I think, like, if you want to view the problem of free will as this problem that exists in a simulation, we're going to try a bunch of different algorithms on it. And so the halting problem may only have bearing on some of those with regard to the problem of free will.
Thanks again for coming and talking. A lot of times we talk about free will in terms of like we can stop this from happening or we can make something else happen. What do we have to say about free will in terms of like large-scale universal events like the heat death of the universe?
Well, the heat death of the universe seems to be pretty inevitable. Once that occurs, I would argue that then there is no more potential for free will because there's no potential to do anything anymore. So free will may be something that we happen to be at a stage of the universe that we're lucky enough to possess right now. You have a follow-up?
But in terms of like, can we do anything now because we have free will to change that outcome or have an effect on that outcome?
I would say no, because free will is different from like being able to change the laws of physics. It's not we are God. It's just that within our system, we are presented with choices within the system, and we can choose between those things in a certain way, or the choice. I think in some sense, when people are talking about how this is this actually free will? What I'm talking about, or is it just not being able to tell? I think what it comes down to is actually being able to take responsibility. Because if no one else could have made that decision or decided to do that action, and you are the only one who could have done that by going through the process, then you have the responsibility for it, right? So whether it be a murder or saving a child or something mundane, like that's why I think this is relevant to free will, is because if no one else can actually have made that choice or decision, and it is entirely because of what's happening inside this computer right here, then I think we should hold that computer responsible. Now, of course, there are things that, we know there are systematic problems with certain computers in certain brains that are more likely to do certain crimes, and there are studies of prison inmates that they can predict basically which prison inmates are likely to re-offend once they are released, based on either certain psychological profiles or genetics or other things. And so yes, if we understand an aspect of the brain that we can say, okay, that part of the brain causes this person to act in certain ways, then maybe we don't hold the person responsible for acting in those ways, or at least once we know that, we try to prevent the person from being in a situation where they might act in a way like that. But I don't think, it's that's very different from being able to change the laws of physics. Free will is not about changing the laws of physics, in my view.
In looking at the halting problem or any sort of lack of predictability that we have, wouldn't looking at it from from a fourth dimensional sort of view that anything that was or will be just kind of is, can't we just we can't deny the fact that even though we don't know specifically what it will be, it will definitely be something, and that thing will be what it is.
I think I know what you're saying, which is this idea of the kind of geometric nature of time, right? And this comes from viewing time as the fourth dimension, that basically everything is going to flow, and what happens now is just a picture, and later on, and so everything is geometric in it. And it comes very much from a deterministic view of the universe. If you have quantum mechanics, then you start to have the many worlds problem, and you can still have this geometric picture, but it's just weirder. But I think the whole point is that free will isn't about the fact that there is going to be a decision made at some point in the future. It's about how was that decision made? That's really what it's about. It's about how is the decision made. We know there's going to be a decision at some point in the future. Like coming to this talk, we know as of this point there are people who came to the talk and people who didn't come to the talk, and there was some process by which that was decided. Some of the people were decided by not knowing about it or being dead, or things like that. But the people who knew about it did have a decision to make.
All right, so I know the gentleman there had brought up the heat death of the universe, and entropy is actually something that is endlessly fascinating to me. And I'm because you mentioned in your presentation, you talk about free will as a sort of associated with this idea of unpredictability. And so I've heard entropy in the past defined as unpredictability. So something that is highly unpredictable has a lot of entropy. So I'm just wondering, is that a coincidence, or are these things related? And if they are related, you being the physicist that you are, could you connect those concepts for us?
Yeah, well, I think the thing with entropy is that entropy is maybe less about unpredictability and more about just the fact that there is great disorder. And disorder and predictability, in terms of the state of a system, you can say, oh, well, I couldn't tell you what any particular thing was. But that doesn't necessarily mean that the behavior of the system is unpredictable. A lot of systems with high entropy actually are incredibly predictable, like the heat death of the universe, or like the air molecules in this room. The macroscopic, at least, view of what's happening is incredibly predictable. We have these concepts of temperature and pressure, which are entirely based off of this crazy disordered thing that's happening at the microscale. And so, yeah, predicting the path of any particular air molecule might be really hard, but the actual kind of macroscopic results are very predictable in these cases.
mentioned before that there was certain like actions of humans that you think may not be able to be predicted. And I just think there was a little vague, like what precisely you meant, like maybe like love or like creative decisions. So yeah, I just wanted more elaboration on what you think can't be like.
Oh, this is one of the great aspects of proofs that are existence proofs rather than proofs by demonstration, is that all it says is that there exists, for example, in the case of the Halting problem, all it says is that there exist programs for which an arbitrary algorithm can't, or any particular algorithm can't find and know whether or not they're going to stop. It doesn't tell you what those programs are. And so I don't know. We know from mathematics and computer science that if the brain works as a computer, there are things that the brain could do that if you had an algorithm looking at it, the algorithm couldn't tell you whether or not that is going to actually, like what the outcome of that computation is, so to speak. But we don't know in advance which those are going to be. And that's part of what's challenging about it, is that you don't know which one is going to be the one that's your kryptonite.
Hi again. So this discussion is just extremely fascinating. So the gentleman right over there mentioned the issue of undecidability of free will. So Gödel's incompleteness theorem states that any axiomatic system with sufficient complexity is either inconsistent or incomplete, or it can be proven to be.
Yeah, there will always be like true statements that you can't prove are true, or false statements that you can't prove are false within that system.
So the cards in the Turing machine, for example, they're sets of axioms, right? You assume something, the if, and then you act upon it.
Right.
The then, right? So then an operation can be seen as, or a set of operations can be seen as a set of axioms. So then a program can be seen as a set of axioms. So then how does Gödel's incompleteness theorem kind of connect to the gentleman's comment of the undecidability of free will?
I'm going to have to think about that. I think I'm interested by this idea that you were thinking about the cards as axioms, because they're only axioms if you then say, well, all the things that we can do based on these axioms, there's not much you do with the cards. They're not, you can, if you change the inputs maybe, then there's other things that the results, you'll get different results. But I'm not sure that they're really, it's not like, because axioms generally are things like, definitions about certain things, or what you can or can't do. Like the axioms in group theory say that there is an element that's like the identity, and there are inverses for every element. These sorts of things, which are more general statements about properties. Whereas I feel like the cards of a Turing machine are maybe not in that, they don't function that same way. There is something that's interesting. This is slightly tangential to what you're talking about, but maybe interesting anyway. People have done a lot of thinking about whether or not, because like in the case of Gödel's incompleteness theorem, often there are true statements within a system of logic that you can't prove are true, but if you add another axiom, you can then prove that that statement is true. Now it turns out that then there are other new statements that you can't prove, but you can't prove true or false. But there's a similar thing with the halting problem, which is basically this idea of what if there were a hypothetical program, and it's called an oracle, which could tell you when programs halt or not. And we know from the results that Alan Turing proved that in any oracle, can't be written in the same kind of programming language. It has to be another tier up, like what you were talking about before. It has to be another kind of level of complexity or something above all of the kind of what we call programs. And so then there's the question of, on this second tier, if you have the second hypothetical tier of programs, when do they halt? Does this oracle program stop, or does it sometimes run forever? And so to know that, you need an oracle on like the next level. And so there's this kind of infinite sequence or series of things. And it's very similar to the incompleteness theorem, that basically you can add something to solve one problem, but then you create more problems, basically, by doing that.
Okay, this will be our last question.
So, the European Union commissioned the Human Brain Project. I don't know if there's much about it, but they're making this giant supercomputer in Germany that mimics the human brain, and they actually started to make a lot of progress on it. I was just curious what you thought, like what implications that might have for the research of free will if they do
well, I know almost nothing about this. I imagine they just have a really fast computer, and they're trying to do things that look like neurons interacting. I think what your question is getting at more is kind of this practical sense of where is the boundary, like how much of what we do can be predicted and how much can't. Because that's one of these things about the halting problem, is that it says that there are programs that we can't predict the outcome of, but it doesn't tell us how many of them there are, what percentage of all programs they are. So I think one interesting thing that might come out of this kind of study is to say, well, is it 50% of the brain's activity that is completely predictable and 50% is unpredictable and kind of free? Or is it 99.999 is predictable and there's a very, very small amount that's free? And that is something that I think will be seen through this kind of experiment.
Give it up for Henry again.
Thank you. It's better than the philosophers. But it turns out that science actually does have something to say about this. Science is not going to be quiet. So on the subject of maybe free will doesn't exist, biology and neuroscience certainly have something to say, which I will be talking about briefly. On the area that it may exist, I think computer science actually has some really compelling reasons to think that free will might actually exist. And then physics really just has to do with the universe, whether it's deterministic or not. Physics is not going to address the other part of that as much. But before we get much farther, I think we need to just get a little bit of something out of the way, which is a gross oversimplification, but basically the way that religion deals with this issue of free will and you being able to act of your own accord, even though there's this all-powerful, all-knowing being and deity, is the soul. The soul can somehow exist outside of your physical being and yet still influence it in some fashion. I don't know how this enables you to have free will. God, I guess, doesn't see souls but sees atoms and electrons or something. But that's the idea. You could also take the Greek or Roman approach of just having gods basically be people with superpowers, in which case they don't know everything and you're all right. But let's start a little bit with neuroscience, since that's the first thing I mentioned. This is not a brain, this is a maze. But neuroscience has some things to say about free will, namely that decisions happen in the brain. And that may not seem like a surprising thing, but there's a lot of research that shows that your unconscious brain actually makes.
So you guys are all here tonight to see Henry Reich. He is the founder and host of MinutePhysics. So he makes YouTube videos for a living. The passions arose back when he attended Grinnell College and majored in physics and math. From there, he obtained a master's from the Perimeter Institute for Theoretical Physics in Waterloo, Ontario. In addition to his interests in physics and math, he's also always been interested in videography and filmmaking and art. So he decided to combine those two passions into this wonderful YouTube channel called MinutePhysics. So tonight, Henry will be talking about the physics of free will, and I think I speak for all of us when I say I'm really interested in hearing what he has to say. So please give it up for Henry Reich.
Can you all hear me? Is this thing loud enough? Is that working? In the back, can you hear me? Sounds good. All right. Let's see if we can get this thing to turn on. There we go. Apologize, the projector seems to have a problem displaying colors in alignment, but most of the talk's in black and white anyway, so it doesn't matter. If you came to this talk tonight, you probably had to make a decision to come here. You heard about it, or maybe your friend dragged you here, or maybe you organized this, makes decisions before your conscious brain is aware of them. There have been studies where people are asked to press a red button at a random time, or with a certain hand, their left hand or their right hand, and the researchers are monitoring their brains with electrodes or fMRI or something, and the researchers can see when the people decide to press the button sooner than the people are aware of deciding to have pressed the button, and the researchers can thus predict. So this makes us question, is free will, if we can tell based on your brain, looking at it before you even know what you're doing or what you're going to do. But then you can ask, well, who are we? Are we just our conscious brain, or is our conscious brain just the part of our brain that looks at what the rest of the brain is doing? And of course, if that's the case, then it's always going to be behind the times because it's just watching what everybody else is doing. And I personally think that I am my entire brain and body, and not just the conscious part of the brain that may be, a little bit late to the party some of the time. So, the other thing that neuroscience seems to be telling us is that all of the things that brains do can be explained at some level by physics. What I mean by that is that brains are made up of cells, and cells are made up of molecules, and molecules are made up of atoms, and protons and electrons, which are governed by the laws of physics. So, in principle, everything that we're talking about here in neuroscience comes down to some aspect of physics. So, let's talk first about Newtonian physics, which is deterministic. This is the traditional, F equals ma physics, or if you want to rewrite that, basically it says obliged to be here, or perhaps you were threatened at gunpoint. But whatever the case, you are here. You made a decision to come here. You may not know why you made that decision. Maybe that no one can know why you made that decision, but you considered for perhaps a little while, perhaps a really long time. At some point, a decision occurred, and you are here. I'm inferring this because you're sitting here. Unless you arrived unconscious on a stretcher, or you're just waking up and wondering what all these people are doing here right now, you decided to be here. Thank you. So I want to talk about why we are here. And I'm talking about literally why are we here. I'm curious, just to do a quick poll before I even begin, how many of you think that free will exists? Surprisingly large number of hands. How many of you think that it doesn't exist? All right. Now I'm curious, how many of you think a definition for free will exists? Because I think this has a lot to do with whether or not you think free will exists. Not very many people think that you can define free will. Well, hopefully we will address that later today. Does anybody have any ideas or thoughts for, can you just shout out, what does free will mean? Be able to act in accordance with your desires. Anything else? No one else has any ideas for what free will might mean?
You can act without any other force upon you.
All right, you can act without any other force upon you. Those are kind of the basic ideas I think that people think about, right? Free will has to do with also, I think, responsibility for your actions, being able to take responsibility for your actions, that they came from you and not from somebody else forcing you to do them or something else forcing you to do them. Which is why we care about free will, because the justice system relies on being able to hold people culpable. And if there is no free will, then maybe you can't hold people culpable for their actions. Anyway, we're going to talk about free will, but first I need to say that I am not an expert in most of what I'm talking about tonight. I draw stick figures for a living. I happen to have a degree in theoretical physics, so the parts about physics that we're going to talk about, I know more about. But I'm also going to be talking about a lot of other things that are outside of physics. That's just the disclaimer. There's kind of, the reason I think people care about free will is because it seems like a paradox, right? We seem to be able to take action of our own accord and do decisions, whether good or bad things. I don't recommend this decision, at least not from that close. Get your friend to be that person and you can watch from a distance. But the paradox is that it seems like either an all-powerful, all-knowing deity, if you believe in God, or a deterministic physical universe, if you believe in science, those things both seem to suggest that free will should be impossible. So we have a feeling that we experience this thing, which is that we can make our own decisions, and then whatever you believe, it seems like maybe it's not actually possible. So if you take those two things together, you end up with 4 possibilities. One is that you think, either you think free will doesn't exist or you think free will exists. And then either you think the universe is deterministic or you think the universe isn't deterministic. And there's some, philosophers have different names for each of the things in these boxes, and that have to do with liberalism and all sorts of fancy words. I think that I'm just going to throw up some random words that I think fit these categories.